So I'm Gabriel Mason-Williams, and today I'm going to be presenting DisTRaC, which is Distributed Transient RAM Ceph, for accelerating high-performance compute processing for temporary data storage. So before we get into that, I'm going to give a little bit of background about the Rosen-Franklin Institute and who I am. So the Rosen-Franklin Institute is a United Kingdom research institute dedicated to developing new technologies to tackle important health research challenges. We're based in Harwell campus in Didcot, and we're funded by the UK ESPRC. We're situated of 5 themes: the artificial intelligence and informatics, biomass spectrometry, correlated imaging, next generation chemistry, and structural biology, all of which generate an awful lot of data. And then myself, I'm currently a master's student in artificial intelligence at Queen Mary University of London. I'm working as a research software associate at the Rosen-Franklin Institute. I'm also looking for a PhD. So, background to the project. This project has spanned many years and has had many people's involvement. It originally started at Diamond Light Source, where it was inspired by Mark Basham and Dave Bond, who came up with the idea behind this. Then it's had involvement with the FCFC Ceph user group, and then recently the University of Bristol have started collaborating with us on it. So, today we're going to go over the background to the problem, then what the problem is, what is DisTRaC, why DisTRaC and not another deployment tool, how DisTRaC works, how DisTRaC solves the problem presented, DisTRaC's workflow, and then I'm going to present 2 case studies where we've used DisTRaC to improve the performance of HPC applications, and then leading with a conclusion and then time for questions. So background to the problem. So this is how a traditional HPC cluster is set up. You have a job scheduler, which schedules different applications onto the compute cluster. So if we had a job that required 2 nodes, it would wait for there to be the relevant room and then allocate said nodes. Then you have the compute, which is often comprised of lots of RAM. Then you have the storage, so a central storage facility here that can be any generally a file system. Then you have the networking, which is comprised of the nodes interconnect, so the nodes can talk to each other, and then the nodes connection to the high performance storage cluster. So what's the problem with this? Well, there are a few. So for IO bound applications, they're limited by the network connection to the high performance storage cluster. It's also a shared resource. Therefore, programs that can process at line rate are able to thrash the shared file system, which can interrupt or disturb other users' jobs accessing this file system. Also, any data that is stored here. So intermediate data that's made during processing and has to be written here gets stayed here for the long term. So the issues here is that we could have node 1, say this is running at line rate and thrashing the cluster. This will then affect node 2 all the way to node n, which is not optimal and it doesn't provide good performance. So what's the solution? Today I'm proposing DisTRaC as the solution. So what is DisTRaC? DisTRaC allows the creation of a distributed transient RAM Ceph cluster. It's a program for deploying a transient RAM Ceph cluster onto a HPC infrastructure, utilizing the RAM in a scalable and efficient manner. Essentially, we're creating a job persistent and isolated in-memory file or object store for the job application. So DisTRaC's just a deployment tool, so why not just any other deployment tool? So the other deployment tools that are developed in Ceph are often quite slow, as there's lots of safety checks required. They're sequential. They would be over-engineered for this use case. They require SSH, and they're designed to build long-lasting, maintainable clusters, which are not what we need right now. For this use case, it's going to last for as long as the job requires. It's inherently volatile as we're building on top of RAM. So if a node goes down, the process stops anyway. So we needed something that could be quick most of the time, as most of the time using HPC cluster should be used processing, not setting up a storage cluster. So how does DisTRaC work? What's different about its deployment method? Well, it takes advantage of the homogeneous structure of a HPC cluster. And what do I mean by that? We can use MPI. So The DisTRaC level of deployment is that it will deploy the mon node on the head node. It will then place the keys on a network file system. So instead of needing to SSH around and copy the keys, we can take advantage that there's a NFS file system present, such that once it's placed on node 1, all nodes can see it. Then we create the management node. And then this is the point where DisTRaC gets the most speed up, is that we deploy the OSDs in parallel. So the OSDs here on this node are also deployed at the same time across all the nodes, as every node can see all the keys required. This means if we want to build 6 OSDs on this node with each containing 30 gigabytes of RAM, we can do that, and that will happen across the whole way through. And then we can then create the pool, the MDS, or the Rails gateway, and then mount the file system if it's requested. But what does this mean in practice? In practice, it means that the deployment time is roughly 22 seconds or so as you span across. So here we scale from 1 node to 6, deploying 1 OSD per node. Of course, the more OSDs that you set on each node or span, the deployment time will slowly increase because of the way that Ceph allocates PGs. But generally, very quick. So how does the removal work? We take the same process. We apply MPI across for removing Ceph, as we know that all the nodes have Ceph. So this is fine. This is a secure operation. We can then remove all of the OSDs, as we know all of them have the same amount of OSDs and the same structure. And then at the end, we remove the files from the NFS so they can no longer see and they no longer exist. And then we end. And how does this look in practice? Well, we also get a removal time that is about 1.5 minutes. So again, very quick and very efficient. This means that we're not going to be eating into the processing time of setting up the cluster to access these things. So we can now place DisTRaC deployment and removal within the job submission script to create a Ceph cluster in a fast and scalable way that lasts as long as the job process. But how does this solve the problem? So the problem now is moving the IO bottleneck to the node interconnect. So we're now taking advantage of the interconnect between the nodes to create the storage cluster. We've also isolated resources, so these are only accessible from the compute node scheduled within the job. So if this job was able to thrash the line rate of the previous storage cluster when writing to it, it will now only impact this environment here. It will not impact other jobs on the high performance storage. Also, we can now make sure that all the intermediate data processing happens across these nodes instead of the global storage, reducing the IO overhead of the HPC application. So if we look at 2 case studies now, we're going to explore rely on and Savi. First of all, what is rely on? Rely on is a cryomicroscopy structured determination program used at the Rosen Franklin Institute. It uses whole node cluster allocation, producing small intermediate files, and can negatively impact other users' jobs running elsewhere on the cluster. So when benchmarking this, when testing this and comparing it against DisTRaC, it resulted in a processing time or reduction of 5.51% and a total reduction time of 4.37%. So the total reduction time is lower than the processing time, as it was fairly fast to run, and the deployment of DisTRaC then ate into the performance time. Also, the reason why rely on's performance here isn't incredible is that it's mainly a compute-bound process. So the main advantage that we gain here is that we remove the need for a high-performance file system in the cloud, as we can instead just deploy it using DisTRaC. Then we have case study Savi. So Savi was a tomography reconstruction and processing pipeline used at Diamond Light Source and the Rosen Franklin Institute. It runs using whole node allocation and can run at line rate, producing intermediate files as it goes. It's capable of saturating access to the parallel file system, which can negatively impact other users' jobs running elsewhere on the cluster. So, a normal Savu process is demonstrated in this figure here. So what we do is we place in the initial data and it goes into Savu. We then do process 1, which is dark flat field correction, which is then placed on the high performance storage. We then go over to process 2, which is raven filter, again placed on there, and then process 3, the pagan filter. And then we have the last step, which is the most important step that we care about, which is the reconstruction, which then goes to the process data, which can also be on the high performance file system. Now this data generated here is not relevant once we get to step 4. So once we've done step 1, it's no longer relevant once we're into step 2 and we start processing on it. Then once we've done step 3, step 1, step 2, step 3, and then this final step is the one that's important. And this is the intermediate data here. So if we run it using Savu Dozner DisTRaC, we can instead make sure that all the processing for the intermediate data instead happens using DisTRaC Ceph, as represented here. So now the processing happens on the Ceph within the nodes, Ceph within the nodes, Ceph within the nodes, and the last step, which we care about, is done on the global high-performance file system. This results in an overall processing time reduction of 8.32%. However, it reduces the I/O overhead by 81.04%, whilst utilizing the same amount of nodes within both setups. This test and benchmarking was done at Diamond Light Source. So, to conclude, DisTRaC is a Ceph deployment tool that creates a hyper-converged HPC cluster for the duration of a job by utilizing the RAM of the compute nodes. As a result, DisTRaC reduces the I/O overhead of the network file system and offers a potential data processing performance increase, depending on the file system that you're using underneath. The other unique advantages to this method is that we can now select whether we want to use an object store or a file system. So this last step could instead be writing out to an object store instead of the global file system, or a remote store instead. These are the references. Thank you very much for listening. Are there any questions? Hello?
Somebody has a question in the chat. Stefan says, do you use CephFS for this?
So we use Ceph natively. For the Savu example, we use Ceph natively. So using RADOS as the connection mechanism, communication mechanism. And then for the rely on, we use CephFS. So Savu is mainly dealing with image data. So object stores is a more efficient mechanism for dealing with the data. At the moment, we don't scale the MDS servers on each node, but this is something that could be added. So the pool size, it's implemented so it auto scales, so the user doesn't need to state or have any information about the pool, and it's done on the amount of OSDs. But essentially, the replication is set to 0, so the pool size isn't the most important factor in the performance. Because we're running on RAM, we don't care about whether the system goes down, because if one node goes down during the processing, then that processing ends anyway because it's utilizing MPI. So local NVMEs could be used. We haven't implemented it such that it can deploy onto local NVMEs as well, as we haven't had access to any nodes to do that development. As we need to make sure that the nodes, the local NVMEs aren't currently being used. whereas the RAM, it's a lot easier to do that check.
I guess one part that remains unanswered is how much RAM, like in total, would you typically need on each node for to do this efficiently?
So it depends on the process that you're running. So for the Savu, for that application, we used 80 GB of RAM on each node. So that was approximately half the RAM that was on the cluster node. We don't often go over half the amount of RAM on each cluster node for stability reasons, as the processing also will require some RAM.